last time. So let us continue. Last time, if you remember, we kind of went through the whole description. We covered how you describe a signal, a random process in the amplitude domain, and we said you need a PDF for that. And then also how you describe the system in a time domain. And we said that you can do that through autocorrelation function, or what is dual of the autocorrelation function is its Fourier transform, which we call power spectral density. Now, I noticed going through the notes before the class that I actually don't complete don't say it. At the end of all of this, the prime reason why I actually went through all of this. And this is, I don't define when do we say that the signal is stationary, in a strict sense. So let me just put that definition. So x of t is stationary. Let's say this is a random process. And we say x of t is stationary. And there are two conditions. One, PDF of x of t is only PDF of x for every t, meaning that the distribution of the signal magnitude in the amplitude domain does not change over time, right? So what I expect to see as a distribution at any given time is the same. Remember that picture that I had, where I look at the realization of this is the various realization of the random process, x1 of t, x2 of t, and so on. If I freeze the time, my amplitudes become random variables, and I can attach PDF to any random variable. The PDF that I obtain at this time is going to be the same as the PDF that I obtain at any time, right? Doesn't matter what is the time that I look, the distribution of the signal in the amplitude domain is going to be the same. But that's not enough condition for the stationary. The second condition is that R, autocorrelation function t tau, is just Rxx of tau. Remember how we define autocorrelation function? We define autocorrelation function Rxx of t tau as expected value of x of t minus tau. And if you really want to be proper, you put the complex constant. Now, this function in general is a function of two variables. One is the time, and the other one is tau, the separation between the two samples. So I'm looking at the product between two values that are tau apart. Well, if that product is only dependent on how far they are apart and not dependent on t, then I have a stationarity in the time domain. My autocorrelation function does not change. And x of t is stationary if it is both stationary in the amplitude domain and the time domain, right? You follow? Right? It's or alternative to this, which is equivalent, is that your x of f or s x of f, which can be also function of t, is just sx of f.
Oh, that's not.
Right? So your power spectral density does not change as a function of time. So the signal is strictly stationary if both of these are whole. It is wide sense stationary if the power if it is just the first two moments that are preserved here. We don't require entire PDF. But even for the wide sense stationarity, we require that this holds. So a lot of books, you read these books, a lot of them kind of take this given, and very few books actually go through the length of explaining where all of this comes from. So hopefully what we went through this will benefit you in other classes. All right, so let's go back to the exact thing where we stopped the last time. We were looking at how does the random process travel through a linear system. And we had this block diagram. We had the random process at the input, and then we had linear system, which LTI, linear time invariant system, our good friend. Because most of the time we try to model everything with us and don't go to anything else unless this fails, right? Because we have a really nice math for all of this. Well, how do we model LTIs? We model them with either their impulse response or their frequency response, which are Fourier transform pairs of each other. And then we get y of t. Now, in this graph here, x of t and y of t represent random processes. We know that for any given x of t, I can easily calculate y of t as a convolution between x of t and h of t. But what I'm really concerned about here is how does the random process travel through the linear system? And what we've learned last time is that we can describe that by looking at the power spectral density of the output, and we can say the power spectral density of the input is your h of f magnitude squared times sx of f. So we see a linear system as largely acting upon a power spectral density. It's modifying the power spectral density of your input signal. Now let me put some additional equations here that are straight consequences of this, and then we'll look through a simple example that exercises all of these formulas. Let's take a look at the power. Right? What do we know about the power? How I determine the power of the signal is by definition in the time domain. This is a limit when t goes to infinity, 1 over t, integral over t, magnitude of x of t squared dt. In other words, the power is the average of the magnitude square of a signal. So that's what we know about time domain. But we have all of these beautiful things in a frequency domain. How do we calculate the power by knowing, for example, power spectral density? Well, here's what we know. We know that our Rx of tau, for tau equal to 0, or in other words, Rx of 0 is what? Is the same as the power. The value of the autocorrelation function for the 0 leg is the power 2. But we also know this. Rx of tau is equal to inverse Fourier transform of Sx of f. Where is this coming from? From our Wiener-Khinchin theorem. Remember, that was the central theorem we quoted last time. Now let's expand on this. This is integral when f goes from minus infinity to plus infinity, Sx of f e to the j 2 pi f tau d f. Right? That's just writing what the inverse Fourier transform stands for. So now, if I use this property and this expression here, you get that Rx of 0, which is the same as the power, is equal to the integral f goes from minus infinity to plus infinity Sx of f. All right. How gorgeous is this relationship? It tells us to calculate the power. You know, the power is smeared across the frequency axis, like a peanut butter thing, and then all you got to do is scoop it up. And this is what this says. You know, you can determine the power of the signal by looking at the area under the curve of the power spectral density, essentially aggregating all the power in the individual sinusoidals that are building this particular signal. This is if your f is a variable. Sometimes this Sx is given in terms of omega, right? Angular frequency. A lot of times the Fourier transform is given in terms of omega too. So an equivalent expression, you would find this one in many books, is 1 over 2 pi integral when omega goes to minus infinity to plus infinity Sx of omega d omega. This is the same expression, but omega is equal to 2 pi f, so you would find this one or this one. In this course, I prefer us using f because everything is symmetric if you use f. Right? But nevertheless, majority of books that are outside of the communications area, I think your linear system book used this expression most of the time. These two are equivalent. So, okay. So let's look at an example. says consider a random process with power spectral density Sn of f given as some n0 over 2 for every f. So this is a process that has a constant power spectral density. We have a name for that process. How do we call that process? White noise, right? So this is a typical way how we model white noise. We say that this process is passed through a filter with the following frequency response. H of f of the filter is given as 1 over 1 plus j f over f0. This is obviously filter. It's a linear system. What type of a filter are we dealing here? How do you check that? You know, when I ask that, how do you check? That's what I want to see. What's the process? You test it. Like, what is the value of this for f equal to 0? 1, right?
1.
So it's not a bandpass, because bandpass is 0 at 0, right? So what is the value of this when f goes to infinity? 0. So this is a low pass filter. It passes DC and attenuates high frequencies, right? What is the order of this filter? First order. First order bandpass filter, low pass filter. And what type of the filter this is? So with the first order, low pass, they're all the same type, but this could be like a Butterworth filter. Okay, so that's so the question here is, if you have this filter, calculate the power of the process after it's passed through this filter, right? So we're given that you have a filter here. We're given straight its frequency response. We have our n of t here, your random process that is characterized with your power spectral density Sn of f, and then you have an output, which let me call it y of t, that will have its Sy of f, associated power spectral density. To illustrate graphically what's happening, and I'm going a little bit slower here because this is the first example, but you know, it will speed up later. And of course, this is our power spectral density of my input. Power spectral densities, we draw it double-sided, right? It's if nothing is said, when you see Sn of f, that means it's double-sided. And you know how you calculate power in a given band. You have to flip it over and then look at the positive and negative frequencies, right? Now, this is Sn of f. Your filter looks like this, right? It's a low-pass filter, so it has this kind of characteristic. It's obviously symmetric, but I don't know how to draw it nicely on the board. And then this f0 here, for f0, your magnitude, your power is going to go 3 dB down. So this is that f0 point, 3 dB cutoff frequency, where the magnitude of the response goes to 1 over square root of 2, or the power goes 3 dB down. So this is your H of f. And we know the relationship that Sy of f is going to be Sn of f, H of f, magnitude squared. So here's what is happening here. You have all of this power of the inputs. How large is the power of the input signal? It's the area under the curve of the power spectral density of the input signal. How large is that area? Infinite, right? So this white noise, there's something fishy about it. It has an infinite power, right? But I'll explain that at some point later in the course. But the input signal has an infinite power. What shows up at the output is this power, right? Area under the curve after it's passed through filter. So filter gets rid of all of these sinusoidals that are outside, and therefore their power too. And the only thing that is preserved in the power of the output signal is whatever goes through the filter, right? Through the bandwidth of the filter. So Now, if I want to calculate the power of the output signal, I know that this is an integral when f goes from minus infinity to plus infinity sy of f df. Essentially scoop up the power spectral density from in the output signal. And in this case, this becomes an integral when f goes from minus infinity to plus infinity. Actually, in every case, magnitude of h of f squared times the power spectral density of the input. But in this case, we have a very easy task. So this is an integral when f goes from minus infinity to plus infinity. Magnitude squared of your frequency response in this case is this. And then your power spectral density of the input is n0 over 2, and then you have df here. And then what I'm going to do is I'm going to divide here by f0 and multiply by f0. So this becomes n0 times f0 over 2. And then I have an integral. Let me call f over f0 as x. Right, so this becomes 1 over 1 plus x squared dx. You can see that this is x squared, and there's another x here. And then when f is, and you realize that this is even function, right, that I'm integrating here. So I can say this is twice integral from 0. When f is so I'm going to say x is equal f over f0. When f is in plus infinity, where is x? Plus infinity as well, right? So this is this. Now, I see that n0, f0. Now, what is this integral? Tangent inverse, right? So this is arctangent of x, where x goes from 0 to plus infinity. So this is n0, f0. And when you substitute plus infinity, what's the arctangent of plus infinity? Pi over 2. Right? How does the arctangent look like? So here's how the arctangent looks like. There's a pi over 2. And there's a minus pi over 2. And this is how it looks like. Right? A little bit better, you can imagine my drawing this. But it's a odd function, right? So now for arctangent of plus infinity is pi over 2. And then for arctangent of 0 is 0. Right? So this is the power at the output associated with this signal y of t. Okay? Any questions? I have a good friend. He would look at this and he would say, it's impossible. Where is the circle? How come there's pi there? Right. Well, pi shows up all the time in unexpected places. Right. So, okay, so I think at this point we're done with the review. That's all the review that I wanted to do. And we need to, there are other topics, and you saw a lot of stuff in that chapter 4. It's a pretty lengthy chapter and a lot of things. But it's good that it's all in one spot, but it's also bad because by the time you get to the place where you really use it, you forgot what you've covered. So at this point, I covered the minimum things that I need. And then as we go, I may actually go back to chapter 4 and cover some additional things as right before we use it. So we're going to talk now, we're going to start with proper digital communication. And every digital communication starts with sampling. So I'm going to first talk about sampling. Then the next process is quantization. We're going to talk about quantization. and then source encoding, and then we're going to go down the line, that block diagram that we had in the first lecture. So let's talk about sampling. Sampling, I said we're done review. Many of you, if not all of you, have seen sampling at least once or twice, or even maybe more than that. So I'm going to go quickly through it, but just kind of talk about bare minimum that we need to look into quantization and move further down the class. So band-limited process and sampling. And sampling. Now that we know what the power spectrum density is, it allows us to define something that we call band-limited process. So if I have a random process x of t is a band-limited random process, if as x of f is identically equal to 0 whenever f is greater than some magnitude of f is greater than some delta. Okay, that's a strictly mathematical definition. It doesn't really become clear until you draw it, right? So this is frequency axis, and this is Sx of f. And what I'm claiming here is that the process is band limited if its power spectral density is essentially equal to 0 whenever the frequencies are outside of this range minus w to w. For the linear system students, let me ask you this. Can a process be really band limited? What's the problem?
No. Finite.
Finite. Beautiful, right? If something is identically equal to 0, that means it's finite in the spectral domain. If something is finite in the spectral domain, it has to be infinite in the time domain, right? But you know, if nothing is infinite in time domain, right? Even universe had a starting point, right? So nothing is strictly band limited in a frequency domain, but at some point there may be a frequency where what is beyond that frequency is not worth counting because it's so small in energy or so small in power that it contributes nothing to the signal. And fortunately for us, majority of the signals that we deal with are like that, right? All of our natural signals are like that, and pretty much all the signals that we deal with are like that. So just let me define what this W is for some typical signals that we deal with for some common processes. W is given like this. For voice, we have that W is on the order of 4 kilohertz. For music, W is on the order of 15 kilohertz. And then for video, depends on the quality of the video, but let's go with the analog video. This can be on the order of 5 megahertz, so it's much, much wider. Now let me just you know, this is not, let me comment a little bit on these. This is what we call telephone voice, right? In general, you know, what you need to know, and it's not only for this course, just it's a good bar topic. We hear up to 20 kilohertz from, or let's say at the bare minimum, 20 hertz to 20 kilohertz, and this is when we are very young, right? As we age, our hearing decreases. My hearing is up to 15 kilohertz. You know, yours is slightly better, but what I'm trying to say is there is more room after 4 kilohertz where we hear, yet we claim that the voice terminates at 4 kilohertz. And this is a subject of, this is a result of quite a bit of experimentation. It turns out majority of voice is up to 4 kilohertz. There is some voice above, there's some power spectral density of voice above 4 kilohertz. And you know that very well because if you remember, we already talked about it, but somebody on a telephone sounds different than in person. And the reason is because we cut out all the stuff above 4 kilohertz. And, but we made an engineering decision to do that because the energy in those components are very small. And the loss of fidelity that you get does not impact the legibility of the voice to a great extent. Now, there is still some difference, and you know very well that when you talk to somebody on the phone and they ask you what your name is, or they always ask me to spell it, then you have to say N like Nancy or C like Charlie or whatever, because some of the legibility is lost because it is embedded in these high frequency components that we cut out, you know, about 4 kilohertz. There is a, now if you look at, this was done in the early communication systems because we didn't have that much bandwidth, and we tried to squeeze everything we could out of the copper line and try to multiplex signals and so on. Now if you look at modern communication systems, you know, especially the broadband that we have, voice is just about the smallest bandwidth that we're dealing with, right? If you're streaming video from YouTube, you're getting more than 4 kilobits per second. If you're downloading files, you know, depending on what, how much it is throttled, you may get hundreds of kilobits per second. So we've come to realization that 4 kilohertz or 4 or 8 kilobits or something on the order that carries this signal is actually quite small for the contemporary communication system. And there is something that is now standardized, and you should see coming up in some voice systems where actually W is 15 kilohertz for voice 2, right? And we sample it and we deliver it at much higher rate for some of some gain in fidelity of the voice reproduction, right? And it is not necessary for say delivery of the voice. We've lived so far without it, but it is actually contributed. It comes into domain of bells and whistles, right? Just like you know, I don't know, the rear camera for parking is not really necessary, but now it's coming on every car because it is there to differentiate various commercial offers, and then, you know, it's one of the marketing things. So for this class, I'm going to always talk about 4 kilohertz because it's a dominant way how we process voice and sample and quantize. Music, 15 kilohertz. That's not what is produced by musical instruments. You know very well that musical instruments, you plug the string and it generates all the harmonics that extend beyond what we can hear. Now, for communications, we cut it off at 15 kilohertz, and this is FM radio quality, right? So, and in FM radio, we broadcast music which is 15 kilohertz wide. And then for video, we have so many different ways of encoding video that because video is very different depending on the actually what happens in the image. Some images are very dynamic. Some images are almost static. So depending, we have a very adaptive way of coding video, and it can vary, but it's never above this. This is the upper limit. Now that we have established that the signals can be, or processes rather, can be treated as band limited, then here's what we can do with these signals. We can sample them. You don't have to know the signal as a whole. In other words, you don't have to know the signal at every point. You can reconstruct the signal without any loss of information from its samples. And this is what we call sampling theory. So let's just state that. So this is one of the most important results of the communication theory. A lot of times it's attributed to Shannon, and I guess Claude Shannon was one of the pioneers in this whole area of communication systems. So what it says is this: if I have a signal and it is band limited, let's say it looks like this, then I don't have to know this entire curve, because if you just don't know any of this and you look at this waveform and I tell you, well, I'm gonna give you the value of this waveform in these discrete points, you may think, okay, there's infinitely many different ways how I can connect these 2 points. And that's true if the signal is not band limited. But if the signal is band limited and you sample this often, there is going to be just one way how this connection would work. So let me state the theorem itself. Because remember what we said last time about what does the power spectral density tell us? It tells us what are the sinusoidals that participate in building this. So if you think about the implication of that, that means the fact that this is band limited means it doesn't have this very high frequency sinusoid. Well, what that means in turn is that we've put a bound on how fast this signal can change, right? So if the signal is not band limited, right, say, then it can change much faster than this. I can have it do this. But the fact that it's band limited and I'm sampling above certain frequency kind of bounds me and says, no, it cannot do that because it simply does not have sinusoidals that will allow building this. And if you sample fast enough, it ultimately translates into the only one way how you can connect this, right? So that's where it's coming from. But let's lay down this formally, and then you can see how I still haven't told you how you actually connect it. Right? I just said that you can, right? But let's spell it out, how you do it. So, sampling theory. So, x of t is a random, band-limited random process. Which means that Sx of f is identically equal to 0 whenever f is larger than w. W is the band, right? W is how far does it extend in a frequency domain. Then the arealization of the process let's say x r of t can be reconstructed without any loss of information. From samples taken every TS. This is the timing interval between samples, but TS needs to satisfy the criterion that it's smaller than 1 over 2 W. The reconstruction formula is given by x of t is equal to sum over k, where k is now the running number of samples. And then I can say x of kts, that's the sample at the kth interval, kth point, times sinc 2 times w, t minus kts. And then I have, let me just say x of t here, sorry about that, 2 times w times ts. Right. There's this factor here. This is this is true when ts is strictly smaller than 1 over 2w. If I have ts equal to 1 over 2w, then this factor goes away. Right? And for x of t is equal to sum over k, x of kts times sinc 2w k minus kts. And this is true for ts equal to 1 over 2w. This is, of course, you know, this is a Nyquist sampling at the smallest possible rate, right? Smallest possible rate. The distance is the largest it can be.
I have a question, Professor. Why mostly we dealing with the continuous signals, not discrete, in the sampling, or whatever?
Well, think about it. You know, is music discrete?
No.
How about video? How about speech? You know, majority of the signals, we live in an analog world, right?
Right.
You know, so majority of the signals are coming as analog signals. Now, there are signals that are coming as discrete signals, but you don't need to sample them. You know, they're already sampled for it, right? But majority of the signals where it's our interface with the world, because the world is analog and our computers are digital, we have to do sampling, right? And then this whole analysis that we went up to this point, business of determining stationarity, business of determining PDF, business of determining the power spectral density, this is all precursor to us sampling and moving from analog to digital domain. So, okay, there's a C missing here, right? Okay. Now, one thing that it creates the confusion, a lot of these books, that's why, you know, even people that do this all the time, they always have to go and look up what is really meant by sinc, right? So let me spell it out. It's different in this course than in linear systems. In linear systems, sinc of x was sine x over x. And this is typically how it's defined in math. In this book and a lot of communication books, we define sinc of x as a sine of pi x divided by pi. Right? So that's how this book defines sinc of x. And I don't think, you know, it's you cannot remember which book is which, but I want to actually point this out. So always check, right? This is kind of like, okay, you know, what is meant by sinc, and then you flip pages and then find out how this particular author define sinc.
So is there any like significant difference between?
It's you know, where do they hit 0, right?
Right.
Sine x over x hits 0 as for x equal pi.
Pi.
This one hits 0 for x equal 1. So
Oh.
what you're doing is you're stretching them along the x-axis, right? But you know, in terms of just be careful, right? But there's no other advice I need to give you there. Okay, so let's you know, this is all fine, but it's still math. Let's understand what does this do. How does this work? So here's how we explain this. Let's say I'm given samples of a signal. And you know, I can always sample the signal, right? That's not, nothing restricts me to do that, you know? It is what is key here is, can I reconstruct this signal from its samples? That's the key. Did I lose any information by getting rid of infinitely many points in between those two samples, right? If I know the value of the signal now and the value of the signal here, I can always do that. But can I reconstruct what happened in between these 2 points? And can I do that with certainty that has to be that way, or have I lost certain information? You know, in other words, to say the same thing is, you know, I sample, I can always connect these dots, right? But how sure am I that when I connect them, this is actually what the signal looked like, and I haven't lost any information? Well, the sampling theorem, what it actually teaches us, if you look at what this formula does here, it actually tells you how to connect these points. That's what it explains to you. If you give me the points, I'll teach you how to connect them. And it connects them in a pretty funny way, right? Here's how it connects them. It says, okay, this is your sample point. Put the sink on that point. And the sink would look like this, right? Associated with this particular point. Notice one thing. It is equal to 1 at that particular sampling point, and it's 0 through every other point. So it's not impacting the any other point. And then you move over to this one, and you put sink there. So there's a sink associated with this point. And you do that for every other point. There's no ambiguity at the sampling points, and the sinks didn't impact that in any way, because all of them go through 0 except 1, right? So the value of the reconstructed signal is always going to be whatever you sample at the sampling point. Where the magic here is, all of these tails that are in between these points are going to add up to what the signal looks like. So now when you add all of these tails, you end up with a signal as it really was, and without any loss of information. This black line is not an approximation to the signal. It is what the signal actually was. This is saying equal here, right? So they're equal. Now let me ask you a couple of questions. First one is, and I'm going to rely on your prior exposure to the sampling theory. Why sync? What's so special about sync? Let's juggle a little bit our brain and remember, where is this sync coming from?
Frequency.
Yes.
Square.
It's a Fourier transform of what? Inverse Fourier transform of what?
Square
Pulse. Why square pulse?
Ideal filter.
Ideal filter. Why ideal filter? Okay, so we go back and say, well, what does sampling in time domain represents in the frequency domain? If I sample in the time domain, what am I doing in the frequency domain? Periodic extension. Look at my good students, linear system. Yeah, you take sampling in the time domain is a periodic extension of the signal in the frequency domain. And then what you do by reconstruction is you're actually eliminating all the replicas of the signals, and you're just doing the low-pass filtering with ideal filter, which is a square pulse. So that's where the sync is coming from. Now, the second question I have for you guys is, what is bad about this particular reconstruction method? The very same, thing, and that's that we are reconstructing with a sync. What's the thing that we don't like about sync?
Need the future
Infinite length.
Yeah, it is infinite length in both directions, so you cannot really do it. Right? So the sampling theorem says, yeah, you can do it, without loss of information, but then it says, no, not really, because you need to wait for an infinitely long time, and if I want to reconstruct what is happening here, I need sync that is way over here, whose tails are going to be contributing to this. Fortunately, the tails decrease as the time goes by, so we can say, well, you don't need infinitely many, samples. We can probably truncate the sync, after 10th sample, and it will not be of any significant impact. But still, you know, if you are a mathematician, that would bother you for the rest of your life. It doesn't bother us much, you know, because we know that at some point you need to engineer it. So, but be aware. So we know this gives us a tool, gives us comfort level theoretically, but in every practical application, we're going to have to figure out a way how we reconstruct the signal from its samples. And we might as well, in some applications, do this, right? And then deal with the consequences that we have some sort of distortion. Hopefully, luckily for us, most of the time this distortion is going to be in a higher frequency, so we're going to low pass everything after we do reconstruction and get our signal. But there is always going to be, in practical applications, some sort of reconstruction error here. And we just need to manage it and make sure that it is smaller than what it really matters. Okay? Now that's all I'm going to say about the sampling theorem, because I'm sure you've seen it. There's plenty of that in a book as well. Now let's talk about the next step. You know, when we go from analog to digital, analog world into digital mode, we, you know, just like we describe the signal in two domains, we have to move from analog world into digital world in both domains. In other words, we have to take care of the time, but we also have to take care of the magnitude, right? Because the process, random process, exists along two axes. It exists along the t-axis and along the amplitude axis. Sampling tells us, okay, you don't need all of these points. You can have the points at a discrete time increments. But it says nothing about, you know, the y-axis. As a matter of fact, this can be the value of the sample according to the sampling theorem can be square root of 2, right? And if we need to represent that in a digital computer, you cannot represent square root of 2 in a computer because it has infinitely many points, digits after the decimal point. So we need to perform discretization of the signal in both domains. Sampling theorem teaches us how we make continuous signal discrete along the t-axis. The quantization process tells us how do we actually make the signal discrete along the y-axis, along the amplitude axis. So let's talk about quantization. So,
Excuse me, Professor. I'm still confused with what is the bridge between whenever you want to switch from analog, because you have magnitude and time in analog. So what is the bridge between the analog to digital?
you have to make your signal discrete in two domains. You know, there's no way around it. The signal is analog in two respects. It exists for any t, right? And then along the t-axis, and then it exists for y values within a certain interval. So there's infinitely many values of y that you can have. And there's no such thing as infinitely many values in anything that is computer, right? You have a certain number of digits. So we have to, we sample the signal, therefore getting rid of all of these points in between the samples. But then the next step is look at the magnitude and say, I cannot really represent this in infinitely many ways. I have to have a finite number of levels that I'm going to represent the signal in the amplitude domain. Going from the continuous range in the amplitude domain to discrete number of levels is called quantization, right? And we let me just draw this, right? So here's how this works. You're going to have all of your samples here. There can be, you know, continuous values, but what you're going to do along the y-axis, you're going to say, okay, I'm not going to represent this with the infinite precision. I'm going to assign this to the nearest level here, right? Maybe here, this guy goes to this level, this one goes to this level, this one goes to this level here, right? So instead of having continuous many points along the y-axis, you're going to have a discrete number of points allowed intervals along the y-axis, right? This process we call quantization. And there's two types of the quantization that we deal with. So two types of quantization. We can talk about something that's called uniform and then non-uniform. Where is the difference between the two? We define this here. These are our levels. Let's say 1, 2, 3, I, all the way to n. We define the difference between two levels as delta I, right? How large is this difference, right? We can make that difference same between all levels. So if delta, which is the difference between levels, is the same, then we're talking about uniform quantization, right? And that's the most common type of the quantization that we have. When you build the hardware, you actually almost always build it uniformly to perform the uniform quantization. It turns out that's not the best way to do things, and it results in a distortion of the signal that is bigger than what you could achieve.
Why?
So I'll go through that in the very next lecture. But just to define here, there is nothing that dictates this. I can make these deltas different, and if you make these deltas different, then we're talking not the same, right? Different, right? From level to level. Okay? They are different from level to level. We're dealing with a non-uniform quantization. Now, so that's the first, I guess, way how we can view quantization. And both of these can be either scalar or vector. So let me talk about another way how we can see, another way how we can look at the quantization. I can say the quantization may be scalar or vector.
I want to ask something fundamental, Professor.
Why
we need quantization in sampling theorem? Why
we don't? Sampling theorem doesn't say that these are quantized. As a matter of fact, it requires that they're not. It requires that this is exactly the value of the signal at the sampling time. The problem is of a practical nature, right? The sampling theorem says you can reconstruct the signal from its samples. When you try to do that practically, what if the sample is pi?
Oh.
Right? How are you going to put your pi in your computer? You can't. You have to truncate. From those, even if you have like a 64-bit, it is accurate to 64-bit precision. Beyond that, you have some error, right? So the practical implementation of this requires that this is not continuous, that this is discrete in a number of levels. And that's what the quantization means, right? So now, going back to this, you can make these levels equal. And this is easiest for us, right? If you look at your computers, that's how they work. Your increments are 1 bit on the smallest bit of the, yes, LSB, right? So our natural way to quantize is using a uniform quantization. But there are benefits to be achieved when you do that non-uniform. And you will see that in most practical applications, we actually do non-uniform quantization. Now there's a trick how we can still do this with this, and we'll have to go through that. The other thing about quantization is the difference between scalar and vector quantization. So let me put that here. What is a scalar quantization? You're taking one sample and you're quantizing one sample at a time. So this is one sample at a time. And this is multiple samples at a time. The easiest way to do the quantization is one sample at a time. I give you a sample, you round it off to the next allowable level, and you move on. There are benefits to be achieved when you do multiple samples at a time. Why? We all understand this. If you look at the samples of the signal, if I know this one, I know something about the next one and the previous one. The signal cannot change, especially if I'm oversampling, right? And I do that for reasons we discussed in linear systems. By knowing this sample, I can say something about the adjacent ones. So I can get better, I guess, precision in representing my signal by encoding multiple samples at a time. Now, instead of quantizing one sample, I quantize a single vector. And this is done, routinely in all, for example, vocoders, right? All the systems that are processing voice signal that are concerned about shrinking the bit rate to the minimum possible. Right?
Oh, like WAV to MP3, something like that?
Like EFR or linear predictive vocoders, they're all doing compression. The way how they do compression, instead of trying to quantize every sample, they look at chain of samples and then they say, oh, okay, this is closest to the vector number 5. And then they send only 5. And then the receiver has a book of all the allowable vectors and it goes to vector 5 and here comes all of these 10 samples, right?
But there will be like a bit rate of that, so...
Yeah, so instead of sending 10 samples, you just send number 5. And you and I know what the 5 is. So you go back to the code book and you pull out the whole word that is associated with 5. So that's one of the principal ways how you do the compression in these. You have to do it smart, and there's code books and there's a whole theory. And I'm pleased to say Dr. Kapuska is going to be teaching that, I think, over summer, just the processing of the voice for the wireless communication, teaching all of these vocoders and how...
I think he's teaching that one in this semester, some of
No,
the
he's
theory.
teaching some of the things,
Right.
but this one is going to be particularly for processing in wireless. What I'm going to cover in this course is I'm going to be talking about these two and this. I'm going to avoid vector quantization. It's just, this could fit in the course, and this is a little bit, I guess, outside of the scope. So let me give you an example that we talked about, but let's just put it on the board so that you understand what is happening here in both time and amplitude domain. Let's look at an example. This is landline telephony. Here we have the signal that has W 4 kilohertz, as we discussed. So then sampling rate, Fs, has to be larger than 2 times W, which in this case is 8 kilohertz, right? So we're going to sample voice at 8 kilobit per second, 8 kilosamples per second, right? So 8 kilosamples, 8,000 samples per second, okay? That kind of tells you already that this is a little generous bandwidth, right? Most of the voices contained, telephone voices, is up to 3.4 kilohertz. So we round it off to 4 kilohertz so that we are not really, doing the sampling at a Nyquist rate. So 8 samples per second. The quantization here, we allow number of levels to be 256. So in voice processing, we have only 256 amplitude values that we are transmitting, 128 positive, 128 negative values. So how many bits do we require? Number of bits.
Number of bits is
Right, 2 to the n is going to have to be equal to 256. So how large is n? N is equal to 8. So we're sampling at 8,000 samples per second, and we're spending 8 bits on every sample. So what is the data rate that we're dealing with?
64.
Bit rate? Exactly. Our bit is going to be 8,000 samples
Multiplied by 8.
per second multiplied by 8 bits per sample. B. This gives us 64 kilobits per second, right? And that's what runs through all of our landline telephone lines, right? We represent the voice with this 64 kilobit per second string. This kind of has a name in North American hierarchy. It's called DS0.
Oh, the
DS0, right? This is the smallest multiplex level that we have in a telephone. Now, it turns out we don't dedicate everything to voice. In a North American telephony, we steal 8 kilobits per second and give that to signal, right? So if you look at the 64 kilobits per second, then this is split into 56 kilobits per second for really voice, and then there is 8, right? 8, yeah, 8 kilobits per second per signal.
Why we cannot get like pure 64 rather than we have like signals, we have that's
Well,
very-
signaling, what is signal? You know, if you connect two communication points,
Oh, handshaking, for handshaking, something like that?
well, handshaking, you know that there is a
Dial tone?
when somebody calls you, there's that beep that tells, you know, that there's a call waiting. You know, then there is a caller ID that comes in. You know, all of that needs to be delivered to you, right? So you have to steal from this 64 kilobits per second to deliver this signal, right? Now that's the answer for you. Why is it that when you look at the landline modems, you actually get 56 kilobits per second? You actually get the 64 kilobits, but you know the signaling steals 8 kilobits for you. So the largest data
So
rate that
to
you can get
demolate,
on,
yeah.
that you can get on a modem is dial-up is 56 kilobits per second. The least significant bit is not used because it can be flipped by the system randomly. In the voice, you don't hear it. It's just a little bit degradation of the signal-to-noise ratio. But in data, you cannot afford to lose bit randomly because system just decides to send some signal. Because what that will do, it will trigger retransmission on a TCP/IP, and your throughput would go even lower than 56 kilobits per second. So we just say, okay, here's your signaling. This is the most I can get from the dial-up.
So that's it in North America. How about in the like southern part of America, like something?
In other parts of the world, we actually have this is for T versus E hierarchy.
Right.
You know, in a T1 hierarchy, this is what we do. In an E1 hierarchy, we actually don't do that. We have a separate signaling channel, and then in that case, you have ability to use all 64 kilobits per second. But majority of modems still use 56 because they want it to work everywhere. Right? 56, I'm sorry, 56. Okay, just for a comparison, if you look at, there is something called, or there used to be something called North American TDMA, which is a cellular technology. Of a second generation North American TDMA. used to be something comparable to GSM. Here's what North American TDMA used to do. The signal, the bandwidth is the same. You start with 4 kilohertz. They used to sample at 8 kilohertz, voice again. The number of levels, they used 8,192. So this is 13 bits per sample, right? So they would sample with much higher resolution in a time domain, but then they would feed these samples into vector quantizing, right? Part of the vocoder. And then what vocoder would give is data rate, net data rate of 7.9, or you can say roughly 8 kilobits per second. Now compare this and this, right? What, by using vector quantization, it was, this vocoder here is able to compress your voice signal 8 times, right? And this is extremely important in wireless because we know that the data rate translates directly into the bandwidth that you occupy, and bandwidth that you occupy, you know, since your spectrum is limited, it determines how many users you can serve simultaneously. So if you can shrink the bandwidth, the data rate that is required to represent the signal, you can get more money because you can have more users utilizing particular channel. But this is kind of an indication of how much of a bandwidth you can get by utilizing vector quantization. Contemporary systems go even below, right? If you look at modern, what is called modern AMR, adaptive multi-rate vocoder for GSM, or wideband CDMA for that matter, it can go all the way to roughly 4 kilobits per second. So achieving 16 times compression relative to the regular PC. Okay. Let me assign the homework. Just one problem, 459. What I'll do, I forgot my notes again. What I'll do next time, I'm going to bring the whole list of problems.
So it means that next time we will have like a lot of homework?
No, I'm going to just give you
Like
write them all out. Because some of them I assigned, some of them I didn't. So I'll kind of make an assignment.